first start with that problem. The problem you were saying. So let's do that. So this is a problem about homotopy of maps. Okay. Yeah. Let me just write the question. Yeah, let me just write the question. So X be a topological, sorry, X be a topological space and F and G are maps from X to Sn, sorry, X to Sn such that Fx and Gx are never antipodal, right? Yeah, never antipodal, and show F and G homotopic. So this is about homotopy of two maps into Sn. Yeah, okay, cool. Okay. Yes. S- Gx. Right. Sorry. Okay. Hmm. Yeah, yes, yes. And H comma. Right. Hmm. I don't uh, know, but before that, my question would be like, this is not yet done because you have to. I mean, at least you have not told me that this is always non-zero. Ah, yes. Uh, eh, F and G are not connected by a line segment. But this condition doesn't say that directly. You mean that I can just algebraically verify it? Or okay. Okay, then let me just do that. So, but this only gives me this. So why is this not possible? Yeah, because modulus. Ah, yes. But you said something geometric, right? What was your argument? Mm-hmm. Yes. Yeah, but it need not pass through this pass through the origin. So it's a chord, and this condition is not directly saying that chords don't exist, right? Yeah, is that yeah? Like so. So if this is I mean, so no, no. Yeah, I meant that this condition is not saying that this is not equal to zero, but because okay, my question okay, because fx could be here and gx could be this could be fx and this could be gx, and then you have a you if you have a linear combination, uh oh ah okay, got it. Through this origin because it's not okay. I took a long time. Yeah, got it now. Finally. Huh. So then this is fine. And then your question is if um, yeah, so maybe your first question could be that is Fn minus F homotopic? Is this can this be a question? Is this a question that you asked? Okay. F is from of course this kind of question could be uh, then it is homotopic or no? No. I mean then you even then I don't know. Okay, so S1 or yeah, cos cos or yeah, okay, maybe don't know. Let's see. No, it will not be, and the reason is that so this F will factor through S1. Okay, so the way I should no, but this is already the quotient map. This, this is already a quotient map. S- Yes, the answer will depend on. So if I say based homotopic, if I add and based homotopic definition, should I give the definition? Do I? Yeah, okay. So based homotopic would mean that H is the homotopy. Uh, H is the homotopy between F and G. Uh, one second. I'm just getting a call. हेलो हाँ नहीं नहीं हम नहीं हम काम कर रहे हैं ठीक है हाँ हाँ रख लेते हैं ठीक है रोटी आप लोग लेते आओ ना रोटी भी लेते आओ अच्छा ठीक है ठीक है हाँ, नहीं नहीं हम देख रहे हो आप आना तो यहाँ शंकर से इंग्लैंड से रोटी लेते आना हम कहाँ जाएंगे बाहर है ठीक है रख लेना Sorry, dad was calling. Sorry. Yeah, so based homotopic means the following. So no path. What is path homotopy? No. Yes. So that's a yes. No wait. No path. So yeah. So right. So it's something like that. So when you say path homotopic, then you are saying at all point these two are fixed, but yeah, so let me see if this is similar. So path homotopic means you would have a map from here to here, and at all points these two are fixed. Yeah, so let me just say path homotopic, okay? Yeah. But then you see this only makes sense if you have the interval. So, but yeah, but this is sufficient for us. So we will not say based uh, homotopy right now. Yes, but let's say path homotopic. Yeah. So so 0 and 1 are going to the same point. So then you are just asking if the homotopy always fixes, it always takes 0 and 1 to 1, right? And then the answer is no. For this F, the answer is no. And yeah, the proof of that is not trivial. Let's see how we can prove that. So of course, a quick proof is the fact that the fundamental group is of. Yes, so let's try to use this. Then if you know that, then we just use it. So how we can use this? Yeah, so F. So when we say the fundamental group is Z, then what is Z in this case? Z is the equivalence classes of path homotopies from zero. Yeah, so right. But let me just write this. So this Z is of course equivalence classes of path homotopies uh, of loops. So loops misunderstood. So 0 and 1 go to the same point, right? Okay. So that's okay. So in this, just say in this. eh, Yeah, sorry. So this, okay, pi 1, because it's the first fundamental group. Yeah, so under this isomorphism, you could say that this f will go to 1, right? That, so that's a part of the proof that what the isomorphism is, right? That this f goes to 1, and then you know that minus f, uh, uh, are you sure minus f goes to minus 1? So I don't know. Hmm. Yes, so put a question mark. Let's see, let's try to answer that. Sorry. So this minus f does not even start from the same point. So we are saying so path homotopy answer is no, because they have different endpoints to begin with, right? Because minus f of 0 is of course, yes, because it's minus 1 comma 0, and that is 1 comma 0. So that's why, yes. So this, so in that way, the, so I'm saying, so I took the wrong question. I took it path homotopy is not the correct condition. So then, yeah, basically we should then just ask if they are homotopic or not. So the question still is the same. Uh, yeah. let's see. Okay. Mm-hmm. Right. homotopic to minus G and minus H. Yes, that is true, but that was not going to be very helpful because this is always true, right? Because any two maps from 0, comma 1 to R is homotopic because R is contractible, means you can just take straight line kind of homotopy. Convex, yeah. So this is not going to be, but yeah, it will imply, right? Because in every coordinate you will be, so it implies, but it does imply, of course, but it's not useful here. Yeah. But yeah, so minus F goes in the other way, right? And F goes F, uh, no, sorry. So minus F goes like this and F goes like this. Goes- Right. So the answer should be no. Uh, but the problem is that now you are minus F. Minus F? Yeah, minus F. Yeah, now what I was saying is the problem is that if you're not going to fix the base point, then homotopy is a very loose thing. And then, okay, then I think it might be, okay, then let's see. So if you're not going to fix the base point, then I make a claim and let's see if it is correct. F is homotopic to 0 or a constant. Is this correct? Then we are done if this is correct. It might be a very, very wrong thing that I just said. So maybe you can think of a homotopy because now you're free. You're not going to fix the base point. So h of x comma t. I think then it is possible because it's like this, and then you can uh, maybe gradually like open it, right? You can gradually sort of remove this over time, but when you do that, and then it will become constant at time one. How do you so on? And then it is not a path homotopy, of course. Um, yeah, so what is the map that takes, so if I take t going to e to the pi, um, sorry, x, x going to e to the pi 1 minus x t. This works. This does it. So I'll just write it properly. X going to e to the pi 2 pi 1 minus x t. This is fine. Yes. Yes. Okay. Yeah. So yeah, right. Then the answer is yes, because then in that sense the space is contractible in, I mean, but sorry, so I should not say that. Yeah, in that sense, every path is null homotopic. Yes, but the space is, of course, not contractible because there is a different definition for that. If we want, we can get into that. So the answer to this is no. So then you can sort of kind of understand that this question, to answer this, you have to put more conditions, right? Yeah, more conditions. But yeah, I mean, sorry, yeah, the answer is yes. Yeah, yeah, the answer is yes. They are homotopic. Maybe I started saying no in between. I'm sorry. So yeah, so if for this one, for the general version, then what do we say for f and minus f? But we do ask these questions actually, that if you have from S1 to S1, then why, how do we ask those questions? Homotopic. Because then none of the points are fixed. They don't have any common points. If you take f and minus f, then there are no points in common. Yeah, so let me just look at my book, algebra topology book. See, because this kind of question is asked, I just want to see the context. I know that there is a context, but for throwing words, I should just see. Or- Yeah, this question is uh, mm, self. So if you take f to be a map from Sn to, so obviously we take x to be Sn, just like you're taking, yeah, oh, so you're taking, that's the thing. So yes, that that suggests me to, that suggests me to ask, maybe now you can ask, try to think about this question. Now what is it? Now this looks like a more interesting question, even if you don't consider base points. Hmm. Before reading more, maybe you can think about this one. Okay. Yeah. Because now I don't think it will be constant. It will not be. s- s- Because you see, like we were really using the property of the interval, right? That we were sort of shrinking sort of the interval also. in order to get that homotopy. Now we cannot do that. So now, like even without the base point condition, because these two are not fixing the base point, they are not fixing 0, or in this case, 1 of S1 in the domain. I think it should be no. And um, that's a good question. Okay, yeah. So now we are getting into some, yes. So right, into some other aspects of S1. So no, it's not no for all. I'm saying no in general, meaning that it's not. This is not true in general. So there is some map for which this is not true. But yes, but as you just said, basically that's what I'm going to say. The on that is, and this actually you can try to prove maybe G. Okay, so G is not surjective implies G is homotopic to the constant. Yeah, yeah. This is a separate thing. You can think about this later, or you can think about it. But yeah, so basically we are talking about surjective maps. Okay, so FP surjective. Yes, but now to prove that something not homotopic is going to be more difficult, as you can understand. Of course, one way I know is using homology. So, but even yes, yeah, using homology we can do, but then I have to define what is singular homology and so on. And in fact, there there may not be other many easier methods actually, surprisingly maybe. Yeah. Uh, if I call that difficult, I should not maybe in general. Yes, yes, yes. And homology is sort of easier because in homotopy you are like here it is. So here you're just taking all maps from S1 to S1 and just looking at the equivalence relation up to homotopy, not even fixing the base point, right? Then to understand this collection is difficult, right? With when the base point is fixed, then you fortunately get Z, right? If you consider path homotopies, but if it is not fixed, then it's a very strange set. Okay, it's called the of loop space of S1. The collection of all these maps is called loop space of S1. Yeah. Yeah. But anyways, it's difficult to understand. So we would like to get other ways to distinguish. Okay. And that's why so one of the things for that is homology, where we take a topological space and instead of associating homotopy to a homotopy group or loop space, like so for any space X, you can define its loop space, meaning collection of all maps from S1 to that space. Okay. These are difficult things more difficult some in general. So homology is better in that sense because it always returns an abelian group. Yeah. So what should we do? Should we go into homology or should we uh, I don't know what you want. Maybe you want to try this later or yeah, let's try that because yeah. But you can think about this. This may actually have a easier proof. Okay, may actually have an easier proof, which I'm unable to think of. So it's not like that. It's uh, easier proof. So let us see. So let's try to talk about, let's try to see. So homology spaces. Yes. Yep. So basically, so you consider the collection of all topological spaces. You can just say category of all topological spaces. This is not working very well. Topological spaces, and you consider. So this is a functor. Homology is basically a functor or sequence of functors. Or means the word functor right now, if you don't know the official definition, actually we don't need here. It's just saying that it is an association. So and okay, there, then that's then yeah, then that's what it is. Yes, exactly. That's so we want to take a space and we want to associate to it an abelian group for every natural number n. Okay, so, yeah, so there is this kind of functor, but yeah, now there are two things. Yes, if you want to do this from scratch, then it is yeah. So the idea is so the idea is like so this H1 is trying to basically measure the presence of one-dimensional holes, just like your pi one. That's what it is doing, right? So if you take R2 and you remove a point, then the pi one will detect it because it will say that there is a loop which cannot be contracted because of that thing. And it cannot be contracted means it's not homotopic, and the pi one will detect it. Okay. So that is true, but the problem is that the thing about the fundamental group is that it it remembers the direction, right? It remembers the direction in which the loop goes, right? So it remembers an extra thing, but you see that is not really needed. Okay, that is not really needed to detect whether there is this one-dimensional, whether there is this point removed or not. Sure, it's a one-dimensional hole because I mean one-dimensional has to be defined and hole has to be defined, which is even more difficult in some ways. So yeah, probably the fundamental group is the definition. So, but anyways, whatever. Yeah. So the point is that the fundamental group remembers the direction. It remembers the direction, and uh, in that way, or maybe uh, now I'm a bit confused whether the homology also remembers the direction or not. I think it also does. But one thing which is different is one thing which is true is this. So you if you yeah, so something like this, like if you take is comma one and then you concatenate comma two, right? So in general, this may not be homotopic to gamma two concatenated with gamma one, right? So X is a space, and yeah, these two are there. Yeah, the problem is one problem is that you do not see this in S1 because in S1 actually the homotopy group is also commutative, right? Z, so it's abelian, and which means actually it is homotopic. This is it is homotopic in S1. But I'm saying that in general it is not. Okay. So for that, uh, a good way to really understand this maybe is to get an example of a space where pi 1x is non-abelian. Okay. So if you don't know example, then you should have to think about this. Okay, and see. then you can understand that this is not true. And for example, just to say an example without proof, because all these proofs will again, this will again require some theorem. There's a technical subject in some sense, where, yeah, at least yeah, to me, because then if you go via this loop and then go via this, and if you go the other way, then they are not homotopic. And it sounds correct only, right? And so, yeah. And the fundamental group of this, and you can try to prove this and see, find it difficult or not, is this. And this we had discussed, I think, free product. Yes, you can say this is this, but this is not the free group on two letter, but this is the free product of two groups. Okay, so it is like free group, but it is somewhat different. Right, and I think we had discussed that free product of groups. But yeah, this is the universal. This was our example of co-product in the category of groups, right? This was in no, yeah, something like that, but not maybe, yeah. Anyways, so that's a different point, right? But then in homology, we basically forget this. Homology theory is developed in a way that we forget it, and in homology, these two become equal. Yeah. And so, what does it mean? So, homology also stores, so H1x also stores these loops, but forgets the composition is commutative. Okay, is commutative. So that is one thing. Yeah. But yeah, all this is just words. So let me maybe start with a def thing. So we will start with, uh, yeah. Am I audible? Yes, I can hear you. Okay. So, okay. So let us try to, yeah, let us try to start with, yeah. So let's start with a very simple version of homology, which is simplicial homology. Because there is simplicial, then there is singular, then there is cellular. All of them are the same in the end, but this is this applies to restricted kind of things. But I want to do this just to so that we can actually calculate something, and right, yeah, simplicial homology. So let X be a topological space, and it will be actually a simplicial complex, but let me not define it. What I will give an example will be a simplicial complex. So, right. Now I should just give an example, which I will be considering. So it's not an example, but it's take X equal to. So why not take it to be the simplest thing? So let's take it to be S1. Okay. Take X to be S1. Now we want to do something like the CW complex decomposition, but simpler than that, something simpler than that. Okay. So we will say that S1 is a point union. Oh, no, sorry, I cannot do this because I'm in simplicial homology. So I will have to take 2 points. Okay, take 2 points. So you can think of this as like zero simplices. So there are simplices, you can use your whatever intuitive definition you have, or you can take this. Okay, just these 2 points take, and I will take two one simplices. Yes, that's a set of 2 points. Yes, and I will take two one simplices. Thinking of the correct notation, or maybe I will just write this then. 1 and 0 comma 1. Okay, it is this. Of course, since you quotient topology, so maybe 1 and 2. Then we have the natural gluing, where maybe I have to write 1 and 2. Then you have the natural gluing, okay, which is basically that. One second. Sorry, this is very bad notation, but I hope uh, what I want to do is just this, okay, 0 and 1. And this is my one copy of the interval, and this is another copy of the interval. Okay, yeah. I realize that I am slightly because I did not define what is a simplicial complex. Otherwise, I could have just said that it is C2. It's a simplicial complex with two one simplices, and the yeah, component is boundary is common like that, and so on. But since I did not do that, so but I still write this for completeness. But now it's clear. So now you agree that this is S1. You can prove that this is homeomorphic to S1. Okay. So of course, as you can understand that up to homeomorphism, the simplicial homology should not matter, right? And we should get the same homology. H1, H2 should be the same. As you know, they are abelian groups, but they should be same. But it's not very obvious that it is true. I mean, it should be true, but it's not obvious how to prove it. Okay, I realize I have not given the definition yet, but sorry. Okay, now we have to form a chain complex. So again, I'm not defining it, but what I will write through that. So this is called a st- or simplicial complex structure on S1. Okay, or I should just say simplicial complex structure on the space. And then now what I'm going to do right will be a simplicial chain complex. So what is that? So the rule, there's a rule, just follow it for now. We have to take the free abelian group. So again, free groups come in. We have to take the free abelian group on generated by, so how should we write that? Free abelian group, maybe I will write like this. Yeah, let me write like this. So free abelian group, yeah, on the points. And I will explain what these arrows are, but first let me write this here. Again, I have to take the free abelian group on the 0 simplices I took. Now I take the free abelian group on the 1 simplices. And by definition, we have to keep doing this. But for us, you see that they are not there. There are no two-dimensional simplices, which now I'm just giving the definition. There's disks, and three-dimensional simplices are D3. Like this is D1, that's D0. This is D0, this is D1. So like that. But those are not there. But in the definition, it is there. And this is called simplicial chain complex of X. So you can see that it's from X, everything is coming, even though at the moment it's not clear that it's a unique way, right? Mm. And yeah, so this is okay. And now I have to tell you what the map is. So you see, a map from a free group is enough to just say what is the map on the generators. Okay, what is the map on the generators? So where does this go? So as you can understand, we will take the boundary in some sense, right? We will take the boundary. So Yeah, let me just change the notation a little bit. Better if we take this. So of course, I know where to send it. Send it like this. And, sorry. It's the same thing, but it's not set correctly. Sending it here. These are just two symbols which defined above. So now here they become symbols. There they are topological spaces. Now they are here in this complex, whatever definition it means. These are symbols, and in some this is basically a Z module. These are symbols, and your group is freely generated over those symbols. So that's what it is. Okay, so this is where we send, and then the map is defined, and this map is this is boundary operator. Then of course there are others if they were there. Yeah. So this recipe, I yeah, I should have to take a more interesting example to explain this, but for the time being, let's just keep this. You just it's a kind of a boundary, but this minus is coming due to the orientation. Okay, means that we sort of alternatingly we'll have to put. If it was V0, V1, V2, if it was a two simplex, then V0, V1, V2. Then you will take V0, the symbol corresponding to V0 minus symbol corresponding to V1 plus V2, symbol corresponding to V2. And yeah, there are still some other things, but yeah. So this is the map. Now there is a homology from homological algebra, which is basically we will take. So let's see where to. Don't, yeah, so here I'll just define. See. So now H0, there is a zeroth homology of X. Or maybe I should not write X right till now because I have not proved that it does not depend on all these intermediate process, other intermediate steps. So I will just say this particular chain complex that we got out of X. Unfortunately, this also looks like it depends on X. I can put a symbol, but let me just, um, yeah, then I just remove this. So what we are going to take is the homology of this complex. And what does homology of the complex mean? Well, so I have to tell homology where. So 0 means the homology at the 0th position. And what is the homology at that position? It is the kernel of this map quotiented by the image of this map. That's the kind of quantity which you may have seen. So, yeah, yeah. So that kind of thing we consider. So, so what is the kernel of this map? Well, it is this thing itself because that's a 0. This map is 0 because this object is 0. So this, and then we take the image. I'll just write the image. The image is this. So what is this isomorphic to? So I mean, this is what it is, but it is isomorphic to Z. Because you see, this is isomorphic to Z direct sum Z, right? Because as I said, this is the abelian group generated by these, not these two things, not the free group, but this is just the abelian group generated by these two things. So that was Z direct sum Z, okay? And if you want to fill in the gaps, then you have to see that if you write this thing as Z direct sum Z, then you should know that this first Z is this 0 generated by 0, and this second Z is coming from this 1. And this thing is nothing but 1 comma minus 1, right? So Z is co-quotient by 1 comma minus 1, right? Or minus 1 comma 1, whatever. Yeah. and this will be isomorphic to Z, which you can prove. Okay, so yeah, but I'm skipping that, just writing this because that's algebra. So that's a separate point. And similarly, you can compute the first homology, and you can see. So here you have to compute the kernel, model the image. So image is 0. So you have to just compute the kernel. And what is the kernel? The kernel is again whatever isomorphic to Z, because the kernel is generated by the difference of these two intervals. Right? So you see this thing minus this thing goes to 0. Yeah, so that is the thing, and you can say that basically the kernel is generated by that. You can prove all that, and yeah. So what we have seen is that the first homology is Z and the zeroth homology is Z. Yeah, which is the same as the homotopy first homotopy group. Yeah, but of course in general they're not the same. Yeah, but this is just this is the toy example. So this is, in fact, this is the only thing probably I'm prepared with at the moment. So but yeah, this is what it is, and let us just quick, maybe we can try to answer that degree question, right? If we can. I mean, of course, you have to assume some things, but even if we can do it, let's say if we can do it after assuming. So let's say that there is a map, okay? Then because it's a functor, I'll just jump to the nth homology. So I mean, it's fine. You don't maybe know what is the definition, but you know the definition kind of, right? But you may not be able to calculate it. That's different, but it's fine. That's not the point. We just take the nth homology, let's say, and this is also like this. And then you know that this map would be like n going to some alpha, or maybe I'll say dn, because it's a map. Oh, I did not say, because yeah, so the nth homology, just like the first homology is Z, the nth homology also Z. Okay, so you can I can prove that, but yeah, later. And so this map HNF is I'm sorry, yeah, is is equal to n going to dn for some d. Okay, and then this d is defined to be the d is unique, of course, right? This d is defined to be the degree of f. Okay, this is the degree of f. Now there is this fact, which is, maybe we can try to prove this next time, or you can see, I'm just stating the fact right now. So if degree of f is equal to degree of 2, it implies that f1 is homotopic to f2. In fact, it's if and only if. Okay, and let me just yeah, look at this. If this requires the based condition, my um, I 1 second. Yeah, let me just look at it. I think it will not require, but because this algebraic homology is, I've let me just check it. There is this will be called homotopy invariance. Yeah, so if two maps, yeah, if two maps from if two maps f and g from x to y are homotopic, then their homologies are, then they induce the same map on the homology. Okay, so I just read one statement. Now let me see if, yes, it does not require, yeah, it does not require base point, right? So now I'll just say this, yeah. So this is for any map. It does not require base points. Okay. We are not proving this. We are not proving this. Okay. But now if you take the map F from S1 to S1 and you answer the question using these assumptions. Yes. Because you know the, oh, but yeah, but you don't know how to compute the map between the homologies. In induced map between you can compute the homology, but to compute the map between the homologies is not difficult, but we'll not do that now, maybe. And let me see then. So HNF, and you have HN of minus F. Mm, actually, I myself don't know if these are going to induce the same maps or not. I have to compute it. Let me just check it and tell you here. Uh, yeah. So they at least try to give you that idea that this can be done through this kind of thing. Ah, sorry. Oh, it's just on 134. So I'll tell you what the book name is. So so this degree has some properties. There is this, yeah, I should just be able to do this using these properties. Yeah. So this let's try to use these properties. So degree of f composed with g is equal to degree of f times degree of g. Okay. Then yeah, so then you see that you have to just figure out if degree of this x going to minus x is what, right? If you can figure this out, then you will be done. Yeah. Okay. And I can tell you, means I'm seeing it, we can prove this, but it will take some time. This will be n to the n plus 1 minus n to the n plus 1. Okay. So then you see that this in our case, this degree is, this is 1. Is that fine? Yeah. In our case, this, because if you if you believe this formula that the degree of x going to minus x is minus 1 to the power n plus 1, okay, that n is the Sn n, then in our case it is 1 because n plus 1 becomes 2, right? Yes, exactly. For S1, right? S1. So so now you see then this degree is 1, and then if you use this thing, right? Then you get that the degree of this is also 1, right? Right. And now we have that the degrees are same. So we want to say from there that the maps are homotopic, right? But that actually is a non-trivial theorem. It's called Hoff degree theorem, which is part of not algebra. Usually, I mean, it's part of differential topology. So it's use the different tools usually, but I don't know. Maybe it can be done by algebra topology. So the answer is yes. They are homotopic. Yes. You can think about some easier proof and also. Yes, I mean, so you build some invariant, you build some, yeah, you take something very simple like a degree, which is just measuring how many times it's going around. If you think about it, this d is how many times it's going around. But maybe to say that in S2, it's strange to say that in S2. It's difficult to say at least intuitively. But then you sort of take that concept and you take it in S1 and you see what it means and you generalize the meaning. And so, yeah, so you take a physical concept and you make mathematical sense of it, and it starts being useful. It's very nice. Yes. Yes. S- Yeah, whoever did it, not me, of course. So yeah. But we have to build these kind, because you see this is the way, because now you can understand this is the way you will get contradictions in mathematics by building mathematical machine. These functors and all are like machines. You build them. And why do I say machine? Because while building them only you use the previous things that mathematics has already been done, like this understanding of functors, composition, and so on and so on. So then you build, then you can, then it's better. So that's why one talks about one talks in the language of functors and this, that, and homology and so on, because then you can, when then what you are saying is you're standing on top of that machinery, so then you can stand taller. So yeah, this is it. Yeah, yeah. Mm-hmm. Yes, that can be proved. Yeah. Yes, that is true. Yes, that is true. And to understand that, it takes some time. I mean, to see that, maybe, so you have to first prove these kind of things, right? Then you see, I mean, why I'm saying this, because you see any group is built out of things like these, kind of. Yeah, because you take free products and you take quotients. So then you have to understand the analog of taking quotients. But once you understand that, then it is fine. And in fact, as you can see now, you can kind of see that, what should I say? No, I'm saying something wrong, basically. So, just a minute. So, how will I? Yeah, but anyways, okay. So the point is that you take quotients. So you have to understand how to take quotients. Means, do what topological operation implies quotienting of the fundamental group, right? Once you understand that, and that combined with this will, yeah, will do it. S- will tell you that everything. Yeah, it tells you a bit more, but it tells you that it is it's a fundamental group of a two manifold in some way. But you can, yeah, ignore that for now. I suggested Armstrong, but you can look at Hatcher also. I don't know if Armstrong has homology or not. You have to see. Does it have? I don't know. But after that, yeah, if you're okay with that, then just you can just do Hatcher. Yeah. Then you just, yeah, follow it. Yeah, it's a, even I have the book, so with me, if you can see it. Yeah, Indian edition. It's nice. Yeah. Okay. Many things. And if I see, so you, huh? Okay. I know that's, but I think it's this is the first time you are learning, so it's fine, and it's very nice. Yes, yes. Homotopy. Yeah, it's basically, it's sort of a, like, it's a brave move to do homotopy. Because in general, when it's kind of see, like, two things are not same, two things that are not same, but somehow you want to say that they are same. They are, and that is gives you so many things. Yeah. So, okay. And yeah, so that's fine. And then we maybe shift theory, if we can discuss